All right, I've started the recording. So, welcome everybody. Thanks for joining. This is going to be the fifth session of the ML Scalability and Performance Reading Group. Today, Kunjan has volunteered to present the paged attention paper. So, with that, I will hand it over to you.
Thanks, Daniel. Yeah, hi everyone. We're gonna go over the each attention paper. Hopefully everybody has had a chance to read it. Um, yeah, page attention is just to give a high-level summary. It's not a new attention implementation. It's more of an optimization of how, especially like, yeah. Um, if everybody's aware, like I guess part of the transformer is to generate key value vectors for each part, each token in the sequence, and during inference, this page attention itself is more of an inference optimization. So during inference, there are two phases. One is prefill, and other is decode, or it's also called as the prompt phase, where the key value vectors are generated for every single token in the prompt. And this is pretty computationally heavy. Um, and later on in the decode, it's more of a vector matrix multiplication, where you generate the query key value for the new token that's been generated. And you start generating new tokens one at a time, which is sequential generation. As this paper highlights here, that is memory bound, as it needs to hold the entire key value vector cache of the previously generated tokens. So the original optimization is just to have a cache of these key value vectors from previous tokens and to store them. The paper here goes over the memory distribution at runtime. Says 65% of memory is allocated for model weights. This memory remains static during serving. Close to 30% of the memory is used to store dynamic state of the request. The dynamic state here is mostly the key value cache. Uh, and and here what they say is that that the curve of the growth in key value cache memory is staggered for existing systems, and this attention optimization makes it more smoother as over time as requests grow. Um, the where's okay, yeah. It, the paper goes on to set the background for how this key value cache is managed currently, and how it grows. Um, and how it grows. So what is the limiting and how it limits performance? So key value cache is limiting batch size, because as the bigger the batch size, it's the amount of key value vectors that you'll have to store will grow. So actually that limits a bigger batch size will give you better throughput of request throughput, and so it limits your throughputness more directly. Um, the key currently current implementations store key value cache as a of a request in a contiguous memory space, so it's just a continuous memory block. That's because that's what most deep learning frameworks like PyTorch, JAX are require them to be, and when performing operations. Um, so that's actually most model servers compute the required KV cache uh, based at initialization, based on like configuration of the model that's being used, and what on the device that it's running on, and how much memory that's left. It assigns a percentage of that to the KV cache, and depending on that is your your how many requests you can serve at a time, or your KV cache needs to be recomputed. So the authors here propose this optimization because they say that the key characteristic of this memory footprint is that it grows and shrinks over the time because because this is dynamic based on the number of tokens that it's generating. So at the start of its lifetime, the only tokens that have key value vectors are the prompt sequence, and then as the output is generated token by token, this key value cache for an individual request grows. Um, they highlight the two types of memory loss that happens in the current implementation, which uh, is the contiguous memory block that's assigned. There's two types of fragmentations that the authors of this paper highlight: the internal and the external fragmentation. The internal fragmentation is caused due to the fact that most serving systems tend to assign a block, a continuous block of memory, um, physical memory to a request, and this is greater than the memory required for storing the key value vectors of the prompt itself. So at start time, it's less, and then it can grow. And while some serving systems have like parameters like max output tokens, which allows this memory allocation to be more definite, others are less. Others which don't have that, they may just allocate uh, arbitrarily a number amount of space for a request, and then the actual request ends up consuming a lot lesser based on the number of max output tokens for that request. So that's what the internal fragmentation problem is being highlighted here. Pre-allocate a contiguous chunk of memory with the request maximum length. This can result in severe internal fragmentation since the request actual length can be shorter than its maximum length. It also says even if it's known beforehand how much to pre-allocate, the entire chunk is reserved for the whole lifetime of the request. And as I said earlier, that this is memory consumption is not one time; it grows during the lifetime of the request. So you necessarily have this entire chunk of memory for future tokens, which is not being used at that time. So what happens is that when after each iteration of the batch, you're not able to queue in requests, even though there's memory within each request. Currently processed request key value, yeah, cache, because it's already been reserved. They highlight the external memory fragmentation problem, which is basically caused because of the non-uniformity of each request. So the memory requirement for each request's KV cache is not going to be the same, which can cause external fragmentation. Mm, yeah. And then later on, I think I would phrase this as a tier two optimization is that um, currently there's no relationship that's been exploited between different output sequences or between requests. Uh, each request is treated as individual, each output is sequence is treated as individually requiring its own memory for storing KV cache. So there's no reusing of the key value vectors that's being done. Uh, so this is something that they go on to also implement in vLLM, which reduces memory usage by reuse. They give an example of beam search and parallel sampling, which generate multiple outputs per request, but for in each output there's a separate KV cache. In vLLM, they show that with paging, it unblocks the implementation of reusing the partial KV, reusing sections of the KV cache and sharing them. But this is not possible for in the current world, where each KV cache is a contiguous space. To address the above limitations, we propose paged attention, an attention algorithm inspired by the operating system's solution to memory fragmentation and sharing. Yeah, if anyone here who's taken an operating systems class would know about the paging and block sizes in of virtual memory, how virtual memory is implemented with pages and block sizes. Um, Paged attention borrows the same is inspired from that, and it basically makes use of treats KV cache as a system memory and divides it into pages and blocks. In paged attention, the blocks for KV cache are not necessarily stored in a contiguous space. Therefore, we can manage the KV cache in a more flexible way as in OS's virtual memory. One can think of blocks as pages, tokens as bytes, and requests as processes. Yeah, so that's exactly they are drawing the direct relationship with operating systems virtual memory management, where blocks in page attention blocks map to pages. Each token maps as to bytes, and requests are processes. So you can think of it as um, a KV cache group of blocks being pages assigned for a process memory, and individual data being the KV cache key value vectors for tokens. That's bytes. Yeah. So in page attention world, each block has certain number of pages, and there's a limit of tokens that it can store the key value vectors for. And a group of blocks is assigned per request. They go into quickly how this elevates the two problems that I listed before of internal fragmentation and external fragmentation. Um, this design alleviates internal fragmentation by using relatively small blocks and allocating them on demand. Moreover, it eliminates external fragmentation as all blocks have the same size. Finally, it enables memory sharing at the granularity of a block across different sequences associated with the same request, or even across different requests. One, I, I think this is pretty self-explanatory, but one thing that is worth noting here is the granularity of sharing, which is at a block level. So, and if we see earlier in what they said was that mm, blocks are pages. So you can think of it as a section of tokens are can key value vectors for a group of tokens can be shared between requests or between the same request among different output sequences. In this work, we build vLLM. vLLM uses block level memory management and preemptive request scheduling. Uh, yeah. So here they laid out the groundwork for it and how they and what they are going to implement in vLLM and the challenges for implementing it. Let's jump right into the uh, some of the challenges that they highlight for it. Uh, I think I put in some highlights for this. Does anyone have any questions so far?
I have some, but I think they'll be better to discuss later.
Okay. Yeah, I'm gonna skip through some of this. This is just like going over the transformer based. I just put in some things that like if you're from the training world for inference and you can note what the or if it's new to you, it's easier it's good to remember these points. One is that the KV cache for one token depends on all of its previous tokens. So this is why when you are in decode phase, when you're generating one token at a time, it's sequential. Because it depends on the KV cache of all the previous tokens, right? And that's also one reason is that that there's also the position of the token in the sequence matters. So it's not just that the token, if it's the token, same token appearing in different requests, you can't just reuse it plainly. Uh, you have to account for the position in the sequence as well. So that's I wanted to highlight that because we will see later on that in the memory reuse section. Uh, and yes, I said that inference is divided into two phases: prefill and decode. Prompt phase, which is basically computing the KV cache for the entire initial prompt, and this affects basically the output of this is a KV cache for the entire request and for the original request along with the first token. So this is called in if you're benchmarking some production metrics for inference server, you would uh, if and you would look at the time to first token as your metric to measure your prefill performance. Normally, this is more of a computationally heavy process because of, as I mentioned earlier, that it has more tokens to process. But it's easily parallelizable. It's more easier to parallelize this. It's more efficient. It uses has a better GPU utilization because it's matrix multiplication operations. Um, and then there's the autoregressive generation phase, which you may have commonly heard as decoding phase, and where it's generating one token at a time for that request. And this is more of a matrix vector multiplication. It's less efficient. It's memory bound because it has to hold a larger KV cache. Yeah. Uh, it does this is the batch talks about batching techniques which have been proposed in like other papers previously about the continuous batching, which is the iteration level scheduling where a batch of requests get if you consider a batch being a group of requests that are being processed simultaneously. um, when some requests tend to finish earlier than the others or are different phase of their others, then when is the batch being when is the contents of a batch being changed, or like when is a new request gets scheduled into the current batch. Uh, Previously was that entire batch would finish and then you would create a new batch in a more simple way. Later on nowadays, it's more common to just do continuous batching where at every single new token generation across all of the requests in the batch, a scheduling decision is made. So there may be a preemption of a request in the current batch or a request that's finished is as an empty slot, which a queued request can take over. Uh, yeah, there's some nuances here. There's the mixed batching as well, normally, and continuous batching without mixed batching, where you would not have prefill and decode requests running together, and only have prefill requests running. Uh, but it basically the key takeaway here is that all of these techniques are complementary to paged attention. They are not necessary. They're not in conflict with paged attention.
Can I ask you a quick question?
Yeah.
Just want to confirm. So you said in continuous batching, basically a scheduling decision is made at each iteration in the autoregressive decoding process. So as like at each token that is computed for the given set of requests that are being processed, it will then maybe swaps them out and make scheduling decisions in that sense. Is that what continuous batching is?
Yeah.
Okay, got it, got it.
The iteration step is a token. Yeah.
Yeah, yeah.
Yeah. But normally there's also like some implementations only have every request in the batch is in the decode stage, or every request in the batch is at the prefill stage.
I see. Okay.
Yeah. And you can have mixed batching where you can have some section of the request in the batch, basically, as the word self-explanatory. But yeah, some portion of the batch is in the prefill, portions in the decode stage.
Interesting.
Um, yeah, here they go with the memory challenges. Use an example to demonstrate how big of a just so well actually from the previous section, page detention it will It's implemented largely in the, well, you see it more used in the prefill phase, but but the benefits are higher in the decode stage. Yeah. Cache size grows quickly with the number of requests. As an example, for 13 billion parameter OPT model, the KV cache of a single token demands 800 kilobytes of space. Yeah, no, a KV cache shape is normally two times, yeah, I have it here, two times bed size, heads, sequence length, and head dimension. And the total is, as this has calculated, they found out to be 800 kilobytes with the number of layers and the precision. Concurrent GPUs have memory capacities in tens of gigabytes. Even if all the available memory was allocated to KV cache, only a few tens of requests could be accommodated. Yeah, so for example, uh, since OPT can generate sequences up to 2048, KV cache of one request is 1.6 gigabytes. So actually, if you were to take it, if you taken, well, I wish they had given an example here of a GPU and a GPU family and exactly told you how many requests can be stored in the KV cache, limiting your bed size. And essentially, it's not that many. It will be in the hundreds at max. And that the limiting factor here is the KV cache. So the more you reuse, you can have a higher number of KV requests. Your throughput increases. Um, Additionally, given the current trends, GPU computational speed grows faster than memory capacity. For example, NVIDIA E100 to H100. Yep, I did some math here to just highlight that point even more with the contrasting the increases with the memory versus the HBM bandwidth and the InfiniBand bandwidth. Yeah, the flops have increased 3x. The HBM capacity has remained same, 80 gigabytes to 80 gigabytes. The bandwidth has increased 1.64x, and the InfiniBand has doubled. Um, but basically, the flops growth is outpacing the bandwidth growth, which means that the decode phase will will lag behind prefill. Will start to will lag behind prefill in future generations of GPUs. Complex decoding algorithms. This is another problem that the paper already mentioned before with the beam search and parallel sampling, where we have a single input sequence generating branching off or generating multiple outputs. Yeah, and and there's memory inefficiencies here because there's individual storage and there's no reuse. Memory management in existing systems. We've gone over that. They use an example to explain the internal fragmentation due to over provisioning and external fragmentation because of uh, mostly being non-uniform size of the request. Yeah. Here's the key point. The takeaway is that in their experimentation, they found that actual effective memory is only 20.4% of the available memory, which is a lot of wastage because of all the fragmentations. I'm curious, I believe I don't know how they calculated the temporary internal fragmentation, because even if the amount of memory was known at the request time because of the number of output tokens and 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 that amount of contiguous allocated uh, until the request finishes. Yeah, there's some internal fragmentation, but at the end, it's all of it will be used. But as a time factor, there's memory wastage. I don't know how they factored that in. Yeah. So here's they go into their methodology of how they implement paged attention and basically kickstarted this LLM serving engine vLLM, which is actually one of the most popular ones out there. vLLM adopts a centralized scheduler to coordinate the execution of the GPU workers. The KV cache manager if effectively manages the KV cache in a paged fashion, enabled by PagedAttention. Yeah, if you are curious, I think Daniel will post these later. This annotated PDF. I put in the links for this. Here's the scheduler. Everyone see my screen? Your
Yeah,
screen.
I can see it.
Yep. So here's the scheduler. It passes in the cache config, which is like the block size. This is a block memory storage as we'll go in to see later on in the results section what block size is most reduces fragmentation the most, because block size will impact your internal fragmentation. Number of GPU blocks that are available, and the model length. Yeah, and there's other features there's for reuse, just the prefix caching and sliding window. Yeah. This is a parameter that you can pass in to the vLLM's instance. And then you have the KV cache manager, which does the paper says. It manages the KV cache. It takes in, yeah, we can see all the methods in here. Uh, so it's the entire manager of the logical blocks to the physical blocks mapping, and how many blocks are free and available, and when to reset them, uncache them. Yeah, allocating new blocks for new requests. All it provides exposes these methods in here. Appending new blocks to the current request, KB cache. Yeah, all of it's an interface. It's a controller for all of that.
Hmm. Can I? Is this a good point to ask a couple questions?
Yeah, sure.
Um, for the scheduler, if we can go back to that, a couple of things just immediately kind of came to mind. Um, when I hear centralized scheduler, the first thing I think about is fault tolerance. So, what happens if, in the midst of serving, this continuous stream of requests, it goes down for some reason and like restarts? Like, is it still aware of the
What do you
KV
mean?
cache on all the different workers? Like, is it still aware of all the workers?
What
Like,
do you mean that the if the scheduler dies, what happens?
yeah, like if it restarts or something.
Uh, Scheduler is part of the core process in vLLM. So if scheduler dies, uh, yeah, you're shafted. You won't have any. You'll lose everything. Your instance will basically die.
I feel like there must be some handling for this, though, right? Because this is like a production grade system used by a lot of companies, right? So they must have some kind of handling. Like, so because it sounds to me like this is sort of like a distributed system. It's like a centralized scheduler. There's a bunch of workers, like processes running on different nodes, perhaps with GPUs available. KV cache manager
It's
on
not.
each of them.
It's Yeah, no, I want to. It's not a multi-host system. This is a single instance system.
Okay, I see. So the GPU workers it's referring to are all just on the single node. So there might be one worker per chip on the single node?
Device per accelerator per device.
I see. So what if I have a fleet of machines that I want to be used for inference with vLLM? You have, I
Yeah, yeah.
guess.
That's not LLM is not for that. You have to have a higher level abstract orchestrator or scheduler so for that.
Yeah, I see. I see. Okay.
So actually, this is part of the vLLM's roadmap. We're diverting here, but they have a roadmap to transfer KV cache out, uh, to backup KV cache, to store into more persistent storages. Yeah, and
Mm-hmm.
transfer between instances of running instances of vLLM. Yeah.
Okay. Interesting. Interesting. Yeah. Because I
The
was kind of
only
thinking
case
about
of
this. What?
The only case of multi-instance vLLM usage I know is disaggregated serving, where you can have a prefill server, and the vLLM instance would know that it's a prefill server,
Mm-hmm.
and you give it the IP, or I guess a very address of the decoder server, and then the prefix instance host will transfer the KV cache to the decoder
Hmm.
instance.
Do you know
The only
do you know
Yeah.
what if there's like a specific piece of orchestration software used for serving on top of vLLM that if you do have say like 1,000 nodes with H100s that you want to use for serving?
Uh, yeah, yeah,
I
it's
I
Kubernetes.
Yeah,
yeah.
I was gonna say it sounds like it could be solved with Kubernetes, but do people like
Yeah.
literally write their own custom controller for that, or is there's got to be some standardization or something,
I
right?
I think a normal sticky session works.
Sticky session.
So the same user in the same like chat window goes back to the same tokens are getting served and you keep hold the connection open. You basically
Hmm.
just round robin between different servers,
Hmm.
and a given user's connection is what do you call it?
Yeah,
Is
it's
persistent
gone to the
across that
same.
session.
Yeah.
Yeah,
That's right.
but you have a bunch of them and you just round robin them or something. You don't you
Yeah,
don't
yeah.
actually do any sophisticated orchestration of what's on which GPU. You're just rotating
That's
users.
right. Yeah. Actually,
Got
this
it.
is pretty common pattern in all many gateways to have sticky sessions. Yeah.
Yeah, I've
So
seen that
And
that's just
in
the case.
like regular distributed systems, kind of like system design interview kind of questions. But I guess yeah, that's definitely applicable to this as well, especially because the data locality is really important for something like this.
I think the assumption in vLLM I think is that basically you also I don't think you can split the model itself across machines that gracefully. Or if you can, that's its
Y-
own vLLM deployment.
you can. Well, no,
Okay.
you can, but you are right that that is above the LLM's layer. Yeah.
Yeah.
That's not in VLLM itself. Yeah.
Yeah, because we have when I've looked at it, it's you have sort of a a more you if you actually want a distributed system like a very large distributed system with VLLM in it, VLLM is basically like your lowest level. It's the application that actually holds the model.
Hmm.
Yes,
Actual routing and
that's
stuff
right.
like that. You're doing that in whatever your normal router is, which
Yeah. Yeah.
there's 1,000 of them and they all run in Kubernetes.
Yep. Pretty much so. And then they all have this session affinity thing, which you would
It's yeah, it's required because a
yeah,
lot of normal application workloads don't work without session affinity.
exactly. So yeah, this is pretty standard at this point for uh, gateways and stuff to have that.
It does have like multi-node pipeline parallelism though.
VLM does.
E
Yeah.
Yeah. So I th I think for one model you can have a few machines in vLLM, but if you're running it, once you scale it, you end up throwing an actual load balancer in front of it because each one does not it doesn't scale to infinity, which is sort of what you want if you have like 1,000 GPUs. But I could be wrong about that. Just setups I've seen, people are doing normal load balancing in front of multiple vLLM instances.
Yeah, you can also do disaggregated serving, which was just implemented last November, where you can split across multiple instances, uh, and you can transfer KB cache from one instance to the other, the same
Um,
model.
you also have spec decoding. I think they have implemented, although I haven't seen anyone deploy it successfully. But that
Yeah,
involves more than one model
but
being live.
yeah, but is that on the different host? I thought that's like concurrently running on the
I
same host, or
think you can split it across hosts, but I'm not sure. I actually have not seen anyone successfully deploy it yet out of vLLM, so I actually don't know.
Hmm. Yeah,
Wait, why
I've
would
used the disaggregated, but that's the only experience I have with VLLM multi-host.
wait? Can you clarify
And also,
why would you want to split speculative decoding across hosts? That seems like
Because
something that. Sorry, go ahead.
because they have really different requirements. So you
The
can have
different
one
models.
spec decode. Yeah, yeah, they're very different models that might have very different requirements, and so you might be okay with your dumb small model running serving like a billion requests a second, and then your fallback model is somewhere else, and it's going to be slow anyway. So you're okay eating the round trip. It doesn't actually matter if you
I
have to
see.
eat like a much longer round trip in order to actually generate from that one.
I see.
Also, I mean, I assume that the hardware would be requirements are different, right? For the small
They
model,
can be, well,
you
they
can
can.
go on a real.
The hardware can be different, and how you want to load balance it could be really, really different. Where like the small model, you could be feeding a lot more traffic to it on even if it's exactly the same hardware on two separate machines, you could be feeding like 10 or 20 times as much traffic to the small spec model, and then your large model lives somewhere else and it has to scale differently, and it sees less
Yeah.
traffic.
Yeah, it also just seems like
Basically,
to
I
me
just
though the like basically there's like a tight coupling between an instance of a small model and then the large main one, and they're like a tightly coupled interaction, and so it seems like you need like super high network bandwidth and low latency between the small model and large model. So it just seems weird to. I mean, I understand the network traffic pattern is different in terms of the request load it can handle, but in terms of just it seems like it would like limit throughput with
I
your
mean,
going over the network rather than like interhost rather than intrahost.
it will, but I think the expectation is that when you hit the big model, you're already eating so much latency that the latency between the machines doesn't matter that much because you're already off of your fast path basically. And so you keep your fast path really,
yes.
really fast, and then your slow path, you're okay with eating an extra like 50 or 100 milliseconds to fail the spec decode and then start reading from the large model.
Hmm.
Yeah. Anyway, we're digressing a little bit. But just to end this query is that they don't really natively support it. Like I said earlier, for disaggregated serving, you just pass in the IP of a node, and that's how it works as well. Yeah. I mean, Daniel, yeah, like leader worker set is like it uses as well to serve like bigger models. You pass
Mm-hmm.
in the your IP of different of your other node, but it's separate processes running.
Mm-hmm.
Yep. Do you have any question about the cache manager itself? This is just, as I said, adds new blocks, manages the blocks that are in it, initializes them, yeah, for each request. Um, okay, we can go jump to the algorithm. But unlike the traditional attention algorithms, paged attention allows storing continuous keys and values in a non-contiguous memory space. So basically, I think what this is saying, this is the key concept of it, is that the logical keys are contiguous for a request KV cache block, but they map to a non-contiguous memory space. Each block contains the key and the value vectors for a fixed number of tokens. So the unit bit for individual block is a token. Uh, each token has a key and a value vector, and the block size is a number of tokens. This goes into how attention computation is done. It's a weighted sum of the attention scores first with the value vectors. It goes into the implementation of the KV cache manager. The key idea behind the vLLM's memory manager is analogous to virtual memory in operating systems. OS partitions memory into fixed size pages, and maps user programs' logical pages to physical pages. The contiguous logical pages can correspond to non-contiguous physical memory pages, allowing user programs to access memory as though it were contiguous. Moreover, physical memory space needs not to be fully reserved in advance, enabling the OS to dynamically allocate physical pages as needed. Uh, vLLM uses the ideas behind virtual memory to manage KV cache in an LLM service. Enabled by PagedAttention, we organize the KV cache as fixed size KV blocks like pages in virtual memory. A request KV cache is presented as a series of logical KV blocks filled from left to right as new tokens, and their KV cache are generated. The last KV block's unfilled positions are reserved for future generations. So here they say that there's a request KB cache is represented as a series of logical KB blocks, which is the contiguous, which are contiguous. They map to physical blocks, and so because the unit here is a block and a block size, so a block is not sharded, is what they want to say. And so if there's the last KB block has empty slots in it, empty pages, which is what empty tokens is the currency here. It's left. Those tokens are left for future. Those positions are left for future tokens of that same request. So you can't have two requests sharing the same block. On GPU workers, a block engine allocates a contiguous chunk of GPU DRAM and divides it into physical KV blocks. This is also done on CPU RAM for swapping. The KV block manager also maintains um, block tables mapping between logical and physical blocks of each request. Each block table entry records the corresponding physical blocks of a logical block and the number of filled positions. I have some code links here. I'll go into it. This is the block manager. It manages the allocation of the KV cache. A couple concepts here that have been described. The detailed design is in this pull request, like the comment says. I think it's not deviated significantly from that. So it has the block size and the number of GPU blocks and CPU blocks. For each of these, also creates an object of allocator instance for the CPU block and the GPU block. Since then, they have built multiple features like prefix caching, which has led to another class of block allocators. But yeah, so here it keeps track of how many blocks are available, how many blocks are filled, and also, and it creates new blocks when needed. And it allocates blocks to sequences. It also knows what is being stored in the block. So this is really useful for when there's mapping or when there's reuse. So it knows which ones are already stored in memory and could be reused. So there's a key hash. Yeah, just the logical block has a key that maps it to the physical memory. Here I've got the link to the actual allocator. Yeah, it has number of blocks. This is shared between the CPU and the GPU block. The same implementation, different APIs being used. There's types of blocks as well, mutable and immutable blocks, which can be created. And there are these methods that are invoked from the block manager, and they're implemented in the block allocator, free, fork, and append. We'll see them later, and swap, we'll see about what they are used for. Decoding with PagedAttention and vLLM. Walk through. Oh, yeah, sorry, I should say that the key takeaway from this implementation style is that logical and physical blocks, by separating them, you don't have to reserve them for all positions in advance, which basically was the problem with the fragmentation, that you are reserving blocks in advance, and therefore especially it's exacerbated, right? When you're doing continuous batching, you can't put in your batch size is limited because you have requests that are reserved blocks in advance. Manages the memory, how it, these are the steps it does to how it for single input sequence, how is the memory managed. Um, as in OSS virtual memory, vLLM does not require reserving the memory for maximum possible generated sequence length initially. Instead, it reserves only the necessary KV blocks to accommodate the KV cache generated during the prompt computation. So that which is the prefill. So because this is definitive, it knows that this number of in prefix in prefill phase, all of the tokens are computed at once. So the key value vectors are computed at once. So that memory footprint is known, and that's the initialization number of blocks. That's how it's the size the number of blocks are reserved is computed through that. How many tokens are in your initial prompt? In their example, they go through this example here. There are 7 tokens here. The prompt has 7 tokens, so the vLLM maps the first 2 logical KV blocks to 2 physical blocks. In the prefills tab, vLLM generates the KV cache of the prompts and the first output token with conventional self-attention algorithm. vLLM then stores the KV cache of the first 4 tokens in logical block 0 and following 3 tokens in logical block 1. The remaining slot is reserved for subsequent autoregressive generation phase. So as here the block size is 4, each block can have 4 tokens in it. There's 7 tokens in your prefill, in your original request, so you need space for 7 tokens at the end of your prefill to store the key value vectors for it, for the KV cache, and its block size is 4, so the block manager will allocate 2 blocks for this request. And one of the slot in the last most block is logical block is empty. It's reserved for the decode phase. Because as I mentioned earlier, a block itself cannot have multiple requests. Step 2, in the first autoregressive decoding step, vLLM generates the new token with PagedAttention algorithm on physical block 7 and 1. Since one slot remains available in the last logical block, the newly generated KV cache is stored there and the block table's field record is updated. So like pages where we have the field, each page has a field record. So the block table's field record is updated for both of these blocks being filled. At the second decoding step, as the last logical block is full, vLLM stores the newly generated KV cache in a new logical block. So the block manager asks the block allocator to allocate a new block at this point to store the new token for the same request into physical block 3 and stores this mapping into the block table. So when there's a new block being created, a new logical block corresponds to a new physical block, and this mapping is stored in the block table. Globally, so globally here indicating across sequences in the whole entire batch. For each decoding iteration, vLLM first selects a set of candidate sequences for batching and allocates the physical blocks for the newly required logical blocks. Meaning, the previous steps that we went over is done on an entire batch level. So when there's candidate sequences that are being added to the new batch, it will the block manager performs these actions for each sequence. Then vLLM concatenates all the input tokens of the current iteration, i.e. all tokens for the prompt phase request and the latest tokens for the generation phase request as one sequence and feeds it into the LLM. During LLM's computation, vLLM uses PagedAttention kernel to access the previous KV cache in the form of logical blocks. Yeah, I can show this kernel. this is the kernel that they use in their attention.
Looking at this just makes me appreciate Triton.
Yep. It's written in CUDA.
Yeah.
Yeah. vLLM's moving some of its kernels to Triton, actually, as they are more there's, Triton kernels being portable between accelerator types. Yeah.
Hmm.
I've linked this in my annotations. So yeah, feel free to go there. I don't totally understand it right now, so I won't go over it. Here we go back to the process of memory use. During LLM's computation, vLLM uses PagedAttention kernel to access the previous KV cache store in the form of logical KV blocks and saves a newly generated KV cache into a physical block. Storing multiple tokens within a KV block enables the PagedAttention kernel to process the KV cache across more positions in parallel, thus increasing the hardware utilization and reducing latency. However, a larger block size also increases memory fragmentation. This is the internal memory fragmentation specifically, because as I said, each block can only have one request. So if you have a larger block size, essentially you are you're undoing the memory, not allocating memory dynamically, the gain of allocating memory dynamically, because when memory is allocated in blocks, and if your block size is big, then you're reserving memory basically for future, which means that you can't really allocate have new requests in the batch. But the benefit of a bigger batch size is also here in the computation, where you can to process more positions in parallel, and you're increasing hardware utilization. Yeah, this I don't know if anyone has a point about reducing latency. Is this a latency of the operation itself? I wonder, is it like what kind of latency specifically is it, or is it overall latency comment? Because I think in decode, this is not that much of a bigger gain. I can see this being more beneficial in prefill. vLLM dynamically assigns new physical blocks to logical blocks as more tokens in their KV cache are generated, as all the blocks are filled from left to right, and a new physical block is only allocated when all the previous blocks are full. vLLM limits all memory waste for requests within one block, so it can effectively utilize all the memory. This allows more requests to fit into memory for batching, improving throughput. Once the request finish is generated, KV blocks can be freed. This is implemented in the block allocator that I went through earlier. Is methods like swap, free, append. We show an example. Okay, logical blocks of two sequences are mapped to different physical blocks within the space reserved by the block engine in GP workers. The neighboring logical blocks of both sequences do not need to be contiguous in the physical GP memory, and the space of the physical blocks can be effectively utilized. Yeah, so now this is the very basic optimization that they get out of having basically enabling non-contiguous memory use. They go into how this can be applied for reuse and the scenarios where reuse is useful. First scenario here is parallel sampling. In LLM-based program assistance, an LLM generates multiple sampled outputs for a single input prompt. Users can choose a favorite output from various candidates. So far, we have implicitly assumed that a request generates a single sequence. In the remainder of this paper, we will assume more general cases in which a request generates multiple sequences. In parallel sampling, one request includes multiple samples showing the same input prompt. So essentially, this is the key here, is that they share the same input prompt, but they're separate sequences, which means that the authors here are going in the direction of reusing the KV cache for the shared input sequence. Via its paged attention and paged memory management, vLLM can realize the sharing easily and save memory. Figure 8 shows an example of parallel decoding. So here we have an input sequence stored across 2 blocks and 7 tokens initially. The first token being generated is logical blocks, and we can see it's logical blocks, and it maps to the physical blocks as well. Block 1 maps to block 0 maps to block 7, and block 1 maps to block 3, right? And we see that there's multiple outputs being generated for this, and because it's token that's mapped to the physical KV block, it knows when to reuse it. At the generation phase, the 2 outputs sample different output tokens and need separate storage for KV cache. But that's the problem that will be optimized by vLLM. vLLM implements a copy on write mechanism at the block granularity, so you can, for the physical blocks that need modification by multiple sequences, similar to the copy on write in OS. I have the implementation here. It copy on write is basically because a single input is generating multiple outputs. So when there's a new output, it copies the block out to different the logical blocks while keeping the same physical block. That's the key goal here, is that for different sequence, it'll copy the logical block, but these same multiple logical blocks are mapping to the same physical block. Is similar to like having a symbolic link to a file. Specifically in figure 8, when sample A1 needs to write to its last logical block 1, vLLM recognizes that the reference count of the corresponding physical block 1 is greater than 1. It allocates a new physical block 3, instructs the block engine to copy the information from physical block 1 and decrease the reference count to 1. Next, when sample A2 writes to the physical block 1, reference count is already reduced to 1. Thus, A2 directly writes its new generated KV cache to physical block 1. So here it shows that they copy the information from 2 sequences sharing the same input, and one of the sequences copies out its information from a physical block to another physical block, reducing the same reference, and therefore the other sequence can overwrite that physical block. Next, when does A2 directly writes a newly generated KV cache to the physical block 1. In summary, vLLM enables sharing most of the space used to store prompts KV cache across multiple output samples, with the exception of the final logical block, which is managed by a copy on write mechanism. By sharing physical blocks across multiple samples, memory usage can be greatly reduced, especially for long input prompts. Beam search is another use case of memory reuse. In LLM tasks like machine translation, users expect top K most appropriate translations output by LLM. Beam search is widely used to decode the most probable output sequence from an LLM, as it mitigates the computational complexity of fully traversing the sample space. So beam search at each iteration can branch out into different candidates, and the sequence can deviate. It builds out like a tree, and leaves can terminate before, and they don't all terminate at the same time. Essentially, you have sections of sequence that are same that you can reuse. The algorithm relies on beam width parameter k, which determines the number of top candidates retained at every step. During decoding, beam search expands each candidate sequence in the beam by considering all possible tokens, computes their respective probabilities using the LLM, and retains the top k most probable sequences out of k dot v candidates, where v is vocabulary size. Unlike parallel decoding, beam search facilities for sharing not only the initial prompt blocks but also other blocks across different candidates. And the sharing patterns dynamically change as the decoding process advances. So as you can see, sequences get forked at any step, and between forks there's similarities of the shared sequences. Here they have an example of it. As candidates at Here's the key part of this example is how the memory is, where they show the memory being reused. As the original candidates 0 and 3 are no longer among the top candidates, their logical blocks are freed. So even though this sequence itself is, the request itself is not eliminated, and this beam candidate 0 and beam candidate 3 and that step, at this step, therefore their memory can be freed up. And the reference counts for the corresponding physical blocks are reduced. vLLM frees all physical blocks whose reference counts reach 0. Then vLLM allocates new physical blocks to store the new KV cache on the new candidates. Now all candidates shared 0 blocks 0, 1, 3, candidates 0, 1 and shared blocks, candidates 0 and 1 share block 6, candidates 2 and 3 further share block 7. Previous LLM serving systems require frequent memory copies of KV cache across beam candidates. For example, candidate 3 would need to copy a large portion of candidate 2's KV cache to generate, because candidate 3 and candidate 2, yeah, because candidate 3 and candidate 2, uh, they share they share the input sequence block 0. This frequent memory copy overhead is significantly reduced by physical block sharing. Copy and write mechanism is applied only when the newly generated tokens are within an old shared block in parallel decoding. So between the blocks are being shared between different beams, and there's when there is a fork, there's a copy on write that happens where new physical blocks are located to in a beam, and the reference count is reduced for that physical block. Shared prefix. Commonly, there's another memory reutilization in this case. Commonly, LLM users provide a long description of task known as system prompt. This description is concatenated with actual's task input to form the prompt of the request. The LLM generates outputs from the full prompt. So basically, here's the two sequences, sequence A, sequence B. They have the same prefix here. See these 5 here that we see, the sea otter, peppermint, plush, giraffe, is shared between the two sequences. So essentially, for that shared prefix, the KV cache will be the same, and that's redundant computation spent on the prefix. vLLM can reuse that computation, and you don't need to do it multiple times, and you don't have to have memory duplication here. In vLLM, this can be conveniently achieved by reserving a set of physical blocks for a set of predefined shared prefixes by the LLM service provider. A user input prompt with shared prefix can simply map its logical blocks to the cached physical blocks. The prompt phase computation only needs to execute on the user task input. So essentially, if you had this is similar to some agents. I can see this being applicable to agents. Prefix caching is what is called these days, is where you have a system prompt which is standard across requests, because of the use case. For example, in the agent framework, if you have an agent with definitive list of tasks that it's going to perform, then it probably has a system prompt, and every single request has that system prompt as its prefix. Each time in the prefill or the prompt phase, the KB cache for that prefix will be computed, and that will be stored once, and it's also stored and also computed again. So there's computational and storage redundancy that vLLM solves. You can pre-populate that prefix cache and that will save you the computational, and across sequences, across requests, you are sharing the same by mapping the logical blocks for that request to this to the physical blocks, and which gives you the which saves memory. Mixed decoding methods. vLLM facilitates simultaneously processing a request with different decoding preferences, which existing systems cannot efficiently do. This is because vLLM conceals the complex memory sharing between different sequences via common mapping layer and translates logical blocks to physical blocks. Yeah, so because there's a kernel that if we these decoding methods that we just saw, there's request batches that have different decoding methods within them. It's harder to do it because the batch operates on the whole because the operations are on the whole batch, and because the memory was contiguously allocated, physical memory is being contiguously allocated. You can't really mix these decoding methods. But with vLLM, the logical blocks are only contiguously allocated, and they translate to physical blocks that are non-contiguous. So you can have diverse decoding styles, patterns. Yeah, here's something about the scheduling and preemption. As number of requests and outputs grow, vLLM can run out of GPU's physical blocks to store the newly generated KV cache. So as this is a cache, we're going to see some cache eviction, which translates to also preemption here and scheduling. There are two classic questions that vLLM needs to answer in this context. Which block should it evict? How to recover evicted blocks if needed again? They go over how the decision for how they decide which blocks to evict, and the evicted blocks are copied to CPU memory actually. Typically, eviction policies use heuristics to predict which block will be accessed furthest in future and evict that block. And since in our case, we know that all blocks of a sequence are accessed together, we implement an all or nothing eviction policy. Yeah, because for a single request, you need the entirety of its KB cache for all of the previously generated tokens and the input prompt. So any missing data over there is means you can proceed with decoding, and therefore it's all or nothing makes sense there. As furthermore, multiple sequences within one request. So as I mentioned earlier, like the KB cache is our across requests, and in each request has a KB cache block, and within a request there can be candidates that are decoded based on the decoding patterns. You can have like this paper just went over with parallel sampling and beam search. So furthermore, furthermore, multiple sequences within request are gang scheduled as a sequence group. Sequences within one sequence group are always preempted or rescheduled together due to potential memory sharing across the sequences. So as we just discussed, the optimization between sequences is that they can share physical blocks. They can share physical blocks, and they can make reuse of memory, physical memory. That's why if there's any eviction that's being done of physical blocks and logical blocks, it needs to be all or nothing. So they're gang scheduled. So and they have this concept of sequence group. If you're more curious, you can look at actually all of the requests are all of the scheduling is done across sequence groups in vLLM scheduler code. Swapping. To answer the second question of how to recover an evicted block, we consider two techniques. Swapping. This is the classic technique used by most virtual memory implementations. Copy the evicted pages to a swap space on the disk. So in classical process memory implementation, is a disk. That's your backup in inference workloads running on accelerators. CPU memory tends to be generally relatively unused, so it's a good backup. Besides the GPU block allocator, vLLM includes a CPU block allocator. I linked the class for that earlier. We saw that the class name was CPU GPU allocator, block allocator actually. So by default, always there's a CPU block allocator with a GPU block allocator for this purpose. When vLLM exhausts free physical blocks for new tokens, it selects a set of sequences to evict and transfer the KB cache to the CPU. Once it preempts a sequence and evicts its blocks, vLLM stops accepting new requests until all the preempted sequences are completed. So when the physical blocks are exhausted for new tokens, it selects a set of sequences to evict and transfer the KB cache to the CPU. But this request is currently in progress because new tokens are being generated. vLLM blocks accepting new requests until all of the preempted request sequences are completed. So this is kind of not a great scenario to be in because you are waiting for a request. A request can block with the overly large footprint. KB cache footprint can choke up vLLM. Once the request completes, its blocks are freed from the memory, and the blocks of the preempted sequence are brought back in to continue the processing of that sequence. So the preempted sequences are brought back in once the other requests that are once memory frees up in the GPU memory. Note that with this design, the number of blocks swapped to CPU RAM never exceeds the number of total physical blocks in GPU RAM. So swap space on CPU RAM is bounded by GPU memory allocated for the KB cache. So that's the point is that they never, because they don't want to exceed, they don't want, at no point in time will there be the CPU RAM usage will be higher than more than the GPU RAM. For the KB cache, I mean. So they don't want. So because of that constraint, that's why vLLM stops scheduling new requests. So that so 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 that this is not just getting, because when there's no space on GPU, it doesn't want to just accept new requests and add them to the CPU RAM.
I have a quick question about this.
Recomputation. Oh,
So in actual like
am I
production,
not?
hello?
Yeah.
Okay. In actual like
Yeah. Go.
production VLM deployments with Kubernetes, so
Yeah.
if the VLM server will stop processing new requests when basically blocks have been preempted and are in CPU memory until there's no more preempted blocks in CPU memory, then I assume it's just like returning some like HTTP status code that indicates it's like rejecting the request while it's doing that, and then
Yeah.
B is I assume it's then possible to configure like horizontal pod autoscaling to use this as like a metric, like requests per second or something that it's handling or rejecting, and know to scale up. Basically, is that the case that you've seen, or?
Yeah. Actually, it's KB cache utilization. That's what you would do
Oh,
to
really?
avoid this scenario.
Okay.
Yeah.
So it can is that how is that
So
even exposed to the Kubernetes layer?
that is expo that's the application metric that's exposed by vLLM. The KB cache utilization is exposed by vLLM.
I see. And then how do you
Of course,
wire? How do you
both the
wi-
GPU and the CPU, really. Both the GPU and the CPU.
I see. So VLM exposes that application metric to Kubernetes, and
Yeah.
how do you wire that up? Is there like like horizontal pod autoscaler config where you define what metric to use and what the threshold is?
Yes. Actually, there's some cloud products where you can even hook that metric in with your load balancer.
Mm-hmm.
So it can route the requests based on the utilization of, yeah,
Yeah. See,
across
that makes
different,
sense. I
yeah.
see. And so is this all supported? This would be you can do this natively with like a deployment. You don't need any special CRD or anything.
Yeah. Like what you do you mean the auto scaling part?
Yeah, just like deployment with horizontal pod auto scaling, and then above that you would have when you say cloud product, you mean like Google Cloud, like load balancer or something?
Yeah, yeah, yeah. But there is a CRD. There are some CRDs like that do it on gateway. They're like gateway CRDs. Yeah, to do it as well.
Really, the gateway CRD? Wait, are you referring to the one that you've mentioned to me before, or is it a different one? The gateway CRD.
Yeah, that's the one. Yeah, that's the one. Yeah.
That's the one. Okay,
Yeah, the inference gateway. So actually, the KV cache metric was implemented.
interesting. Is that working well in practice?
Uh, I haven't seen usage.
Okay,
But
interesting.
the problem here is that this is not such a it's a problem is response latency. How
Hmm.
fast can you auto scale,
Hmm.
right? Uh, because you have to preemptively auto scale actually if you're looking at KV cache utilization
Hmm.
because it can spike up, right?
So when you say preemptively auto scale, do you just mean like over provisioning?
Like you can't necessarily just wait for the utilization to hit 100 for the GPU KV cache utilization.
Hmm.
You would have to like it can it's not linear growth. It can grow stepwise.
Right, but can
So
you just
like
configure the threshold to be lower than 100, like 70 or something?
yeah. That's right. Yeah. So that's the practice.
Hmm.
And then it's how fast you can respond, right?
Hmm.
Once the metric triggered and the auto scaling is well, the cloud providers don't really can't really schedule very fast.
Hmm. So do
And
they
the other
normally, because not only
thing
because
is
like,
because
go ahead, go ahead.
when you scale it has to route to it as well. So which like something that Kubernetes can do. A Kubernetes service can do that. Yeah.
Hmm. Interesting. Okay, I'll leave it here. I have another question I want to make sure we have time for. So,
Yeah. Yeah. Recomputation. In this case, we simply recompute the KV cache when the preempted sequences are rescheduled. Uh, Note that recomputation latency can be significantly lower than the original latency as the tokens generated. Decoding can be concatenated with the original user prompt as a new prompt. Yeah. But basically, recomputation means you can't just recompute that particular token. You have to recompute the whole sequence from until now, which can be slower. As compute bound, you're performing prefill again. So they have some analysis on when to recompute versus when to swap from CPU RAM. Yeah, distributed execution. Many LLMs have parameter sizes exceeding capacity of a single GPU. It's necessary to partition them across distributed GPUs, execute them in model parallels fashion. This calls so they go where the tensor parallelism that's produced in Megatron LLM. We went over that here. There's specifically attention operator split on attention head dimension. So the parallelism is done across heads, right? Uh, and each SPMD process takes care of subset of attention heads in multi-head attention. We observe that even with the model parallel execution, each model shard still processes the same set of input tokens. Yeah, is each shard processes the same set of the sequence. This requires KV cache, though basically the importance of this fact is that uh, the part of KV cache that's being used for access by a device will be is governed by which tokens it's processing in the sequence. The that for which process is which tokens is computing the attention scores for, and that's why this they're highlighting this that the memory use will be same, requiring the same KV cache for the same position. Therefore, vLLM features a single KV cache manager within the centralized scheduler. Different GPU workers share the manager as well as mapping from the logical blocks to physical blocks. This common mapping allows GPU workers to execute the model with the physical blocks provided by the scheduler for each input request. Although each GPU worker has the same physical block IDs, a worker only stores a portion of the KV cache for its corresponding attention heads, which is the parallelism. So the KV cache is split across the GPUs. But the physical block ID. Yeah,
Okay.
what?
I had a question kind of about this. It's not really specific to model parallelism, but just parallelism in general. I was just thinking about, our last topic was ring attention and how it's used to
Yeah.
support like 1 million plus context length. So if we wanted to, I just did like a cursory Google search and it seems like vLLM is not compatible with ring attention. And that makes sense since this is like a single node focused system. But in principle, I was wondering, okay, what if we wanted to design a system, like say like Google Gemini or something, where we have like 1 million plus context length, but we also want to support high throughput to support like millions of customers. How would we do it? And like, it seems like in principle, this maybe not this specific vLLM like implementation, but the mechanism they're proposing here of basically using like a virtualization layer, like a logical blocks mapping to the physical blocks in memory, and using that to more efficiently make use of our available VRAM. It seems like as you could apply that to the ring attention mechanism of like rotating, like partitioning the KV blocks and then rotating them around between the nodes. I'm just like, I just want to think about that and ask, you and the group at large, if does that seem like it'd be possible in principle, or is there something maybe that would stop us from implementing something like this?
Mm.
Like so the request comes in, it's like say it's like a million tokens of initial context. We do prefill, we have our KV blocks, and then we partition them across the nodes. And as we partition them across the nodes, each instance, maybe it wouldn't be vLLM necessarily, but each instance there could use this page attention mechanism to map those KV blocks to logical blocks, or rather assign them to logical blocks and then map those logical blocks to the physical blocks, right? Then we perform one instance, one iteration of decoding, and then we rotate, right? We rotate the KV blocks, and I'm just wondering if there'd be any benefit at all, huh?
Rotate, you mean in like ring attention rotate, or what do you mean?
Yeah.
Okay. So transfer between like move have one cycle in the ring attention, like move from one node to another node. That's on.
Exactly, but we are also dealing with multiple requests concurrently, like batches of requests, right? So, then we could use something like page attention to ensure efficient usage and avoid memory fragmentation between the physical memory blocks allocated. Yeah.
On. Yeah, I honestly think, yeah, I don't know why that wouldn't work. Yeah.
Yeah, it seems like it would. I saw a GitHub issue in vLLM asking to support for this, but it didn't seem to get much of a response. It got mentioned in the Q2 roadmap of last year, apparently, but was not implemented, and I didn't see any really discussion, so I wasn't sure if it was just like outright rejected for being a dumb idea for some reason that I'm not seeing, or if it just is probably like an extremely involved implementation and they haven't gotten to it yet.
Yeah, I think it's latter. I think seems it probably because vLLM fundamentally is not multi-instance design,
Hmm.
and what it suggests ring attention, you would need that, right?
Yeah.
Because the ring attention falls apart if you cannot hide the transfer between computation, right?
Hmm.
It's- so it really
Exactly.
need to be very lockstep between the different instances.
Yeah, and it also relies on the blockwise transformers where they like fuse the blockwise attention, like flash attention basically with the feed forward and residual layer into like one
Yeah.
kernel essentially to get enough compute time to where it hides the communication of rotating the blocks. And so it makes like I guess maybe not super generic, or I'm just not sure how you would support like an arbitrary model to serve like with a serve like an inference engine or
By the
serving.
way, pay attention only for managing KV cache aspect of the, yeah.
I see. I see. Okay.
But I also think that maybe non-contiguous memory is not great for ring attention.
Non-contiguous memory.
Yeah,
Can you
this is
expand
what
on that?
like page attention is physical blocks are non-contiguous, right?
Yeah.
So there's added step of gathering them before performing the operation.
Mm-hmm.
We can see that actually they have a latency of 20 something like 27% higher than just using normal.
Yeah, like there's some overhead involved. But so it's like a throughput
Yes.
optimization, not a latency optimization. But
Yeah. It's a memory management, memory optimization, and so throughput optimization because of the memory,
yeah.
because throughput is limited by memory.
Yeah, you can have batch more requests
Batch
together.
big.
Yeah,
Yeah.
that makes sense.
Well, I don't know. That might be good for ring, or because you have more computation time to fill in.
Hmm.
But at the same time, yeah. I don't think I think that vLLM's priority from next year is mostly around a lot of it around is from what I can tell from the roadmap is disaggregated serving and prefix caching. They're really big on that. Um, yeah, having more reuse.
I see. Okay, well that's all I had. I have some interesting startup ideas
Yeah,
now, I think,
I
or maybe research ideas.
yeah I linked the kernels that they mentioned here.
Hmm.
Won't go deep in that. I won't claim to understand that code very well. But they're simpler than like some normal kernels. But yeah, they're all written in CUDA. Uh,
Cool.
yeah, there is some latency added to this. So yeah, 20 to 26% higher attention kernel latency. And they also talk about the choice of a block size because it can lead to internal fragmentation. And um,
Hmm.
yeah,
So
there
like
is
a giant
another
block size.
paper. Yeah. Which will like remove the basically because of the giant block size, you are reserving more memory for the request in advance.
Yeah, yeah. So internal fragmentation.
But there is a paper called S-LoRa, um, which proposes building up on paged attention to having a unified paged memory for low rank adapter decomposition matrices, and so that you can have more because the batching problem is also similar in LoRa.
Hmm.
Yeah, because your batch size is held back by how many adapter weights, different adapter weights you can store.
Hmm.
And right now, current implementations of LoRa don't really have paged memory for LoRa weights, so they are there's fragmentation there, same problems. Like essentially, like your request, you can have multi LoRa. This is a problem for multi LoRa. So where your batch, all of if a request A is using a LoRa, a different size of LoRa than a request B, uh, then there's external fragmentation in the LoRa memory because of the size difference, and there's not such internal fragmentation because in LoRa because it doesn't grow like KB cache. Um, but it still has the same effect of limiting your batch, right? Because you don't your if your batch has X amount of memory, how do you divide it between different adapter sizes?
Hmm.
So they proposed that in their S-LoRa paper.
Maybe we can do that one next time, or sometime.
Yeah, you can put that on the paper list. Yeah, and there's also another implementation by the creators of the vLLM actually, Wusok. It's called Radix Attention. Um, I believe the paging aspect of memory storage is same in
Hmm.
Radix Attention. It's more about the keying aspect. So how vLLM does prefix keying is it takes in everything, almost everything about a token, all those metadata like sequence length and what position it's in, and the entire token basically, and that it constructs a key out of it. If there's a LoRa that was used in the request as well, it will encounter it, use that as well, and constructs a key out of that for that key value vector in the memory. And so whenever there's a new request that comes in, it looks for a key, it does a key lookup for that same token, uh, and then if it hits it, it reuses the key value vectors. Uh, in Radix Attention, they instead of a key-based storage, they implement a radix tree storage
Hmm. Wait, why?
to have better prefix hit rate.
I see. Oh, wait, so does that mean you don't necessarily have to have the entire key match, like the entire prefix match rather? You can if like some sub like some contiguous subset like the first like half of the prefix matches, then you can get a hit and just go down each node in the tree until you don't have a match. Kind of like.
Yeah, that is, but that is how vLLM also works. That you don't have to have the entire sequence being matched.
Mm-hmm.
Like it does like your part of your prefix key matches, then it will hit that. Like let's say if you are trying to compute key value vector for attention for token X, it can generate that key for that token X based on its position in the sequence, the previous tokens,
Mm.
uh, and the LoRa adapter for if there is one, and then it looks up that key in the logical table, and then it sees it exists. Then it's if it exists, then it will not compute the key value vector for it. Radix instead does a more I believe they do a tree based approach. Yeah,
Okay.
I'm not sure entirely why it's better. But it is they do say it is performantly better than vLLM.
Okay. Maybe we can put that one on the list for later too. Radix attention.
Yeah. Okay. Yeah, vLLM is pretty good. I encourage everyone to look at the code and try to. The code is a bit messy. Yeah, there's a lot of indirection in it. I'll
Really?
put some links here. Yeah.
It didn't look that bad lately.
It's
The
right.
screenshots I was seeing, I've seen worse, especially lately.
Yeah, no, I mean there's a lot. Yeah, it's hard to trace and there's a lot of indirections. It's not that easy. I have contributed to it. So it was hard. It was the learning curve was hard the first time to
Mhm.
find out where exactly to implement.
Yeah, well, big projects are always kind of like that, right? First, first contributions, kind of learning curve.
Yeah, yeah, and they just have a lot of indirection and you fully use Python for yeah. I mean, I think they have many interfaces and abstraction. Yeah,
Yeah, I've noticed that like moving from Go to Python recently, there's a bunch of like I don't know, like things that like kind of like unnecessary and superfluous use of context managers to where it just makes the code like indecipherable. Like it'll be like with some variable colon pass and then like a bunch of other stuff and you have to like what the hell is this? You have to like go into the context, like look at the context manager implementation, like understand why, like because nothing's even happening in the context manager. So why is this even here?
yeah,
I don't know. That's kind of probably that example doesn't make much sense. Talking about code verbally is kind of tricky, but um, Anyways, yeah.
Yeah, yeah. There's something that's coming up from context, but where is it? Which where you have to locate it in the stack where that is being set in the context, and and because every lot of context being passed around a lot, so it's hard to see who gets that value in the context.
Yeah, and a lot of
Yeah,
what's it called?
it's one of them. It's like they have too many base classes and abstract classes,
Yeah. I
and
didn't even mean context like in the LLM sense. I meant context manager and
yeah, I
like
know.
the oh, you did? Okay,
Context.
okay. Yeah.
Yeah, I know. I was
But
kidding.
what was I gonna say? Also, just a lot of Python code bases, there's not any kind of type hints, and so you just have a bunch of
Yeah,
random variables, and it's just not as clear, like, what is this? You know? Um,
yeah.
but yeah. Anyways, yeah, this was really good. This was very thorough. I learned a lot, especially like on the production side of how, um, the kind of the theory and implementation proposed in this paper for like the single node system, like how it can be used in production at scale. I think it's like a lot of interesting. We had like multiple good conversations, discussions throughout this one. So yeah, pretty good meeting today, I'd say.
Yeah, and I don't want to make sure like that, like radix attention and page attention, and I guess even ring attention that we just talked recently are not like new attention mechanisms, the like group query attention or
Hmm.
but they are multi-latent attention, but more like memory optimizations and
Yeah.
sharding.
Yep, KB cache management to improve memory optimization, improve throughput in your serving systems. Makes sense.
Yeah,
Cool. Yeah, next
serving
time.
optimization.
Yeah. Um, and next time I almost kind of wanted to go over like um, DeepSeek V3 perhaps, because I think it's either V2 or V3 where they introduce multi-latent attention and like multi-token prediction, which are both interesting
Yeah,
from like just the algorithmic theory side, but also are efficiency improvements. So which kind of I think align well with the top like the topic of our group here. So it's kind of like both. I don't know. What do you guys think?
I like that. Maybe we can break up in is the deep. I haven't seen how big is how many new things, how much of a background knowledge is needed for DeepSeek
Hmm.
paper, but we can maybe break up by the novel aspects of it. I don't know. I would love to. I think that would be great to know more about this. It's trending so much.
Yeah. Same. And I like to use this group as an opportunity to, explore those things that pique my curiosity. And I think everybody else is probably also curious just because it's being talked about so much. So, um, yeah, it seems relevant. Cool. All right. Well, I'll stop the recording now and put it on YouTube. Thanks for presenting today. It was awesome. And